We saw how to realize the PMOS common source amplifier, and we analyzed all its characteristics, a small and large signal. Now, every circuit that we know, that is all the different biasing techniques and the control sources, we can derive from scratch for PMOS just like we did for NMOS. But of course, it would be less efficient. What would be more efficient is to systematically convert every NMOS circuit that we know into PMOS, and similarly, if we derive circuits with PMOS, we should be able to immediately write down the NMOS circuit without doing a lot of extra work. Okay, and it turns out that it can be done very easily. Okay, I will take the example of common source amplifier with source feedback biasing, but exactly the same principle applies to any other circuit. Okay, and by taking this example, we also will have illustration of another circuit using PMOS transistors. Okay. We have Vi, Rs, and a coupling capacitor, a voltage divider to establish the gate voltage of the NMOS transistor, the current source at the source terminal to provide bias, and a capacitor across it to short it for signal frequencies. This is the ground, the lower rail is ground. Okay. And at the drain, let me assume that we have a drain bias resistor RD and a load resistance RL, which is connected to ground. Okay, C2, C1, C3, I0, R1, R2. This is the circuit with NMOS transistors. Okay. Now, as you well know, the small signal picture of NMOS and PMOS are exactly the same. The operating points have exactly the opposite polarity. Okay. So, how do I convert this to PMOS? It's very easy. First of all, I identify the sources that establish the operating point, and in this case, that is I0 and VDD. Okay. So, first let's see how to set up the PMOS transistor with the correct operating point. Okay. So all I have to do is, again, because I'm discussing the operating point, I'll set Vi to 0, or in other words, this will be a short circuit. Okay. Now, let me replace this with a PMOS transistor, keeping the terminal correspondences. The NMOS transistor had its drain connected here, gate there, and the source there, and I'll do exactly the same for PMOS. Now for PMOS, the arrow is pointing inwards, and this is what it looks like. Note that this is not how I conventionally drew it. In my earlier examples, I drew the source of the PMOS on top and drain at the bottom. This is the opposite. Because the polarities are opposite in the operating point picture, I replace this with minus VDD, or I can say that this is VDD. Okay. And similarly, this current source becomes minus I0, or it just points upwards. Okay. So this is the operating point picture. Okay. Now, that's all that's there to it. It turns out that now, in this case, the current from source to drain of the PMOS transistor will be I0. Okay. And because we reverse the sign of VDD, the voltage between R1 and R2, and in fact, between any two node voltages in the circuit, will be exactly the negative of what we had before. Okay. And that's exactly what we want for a PMOS transistor, right? Because VGS in an NMOS transistor is positive, VSG in a PMOS transistor is positive, or VGS is negative, and so on. Okay. Similarly, the current flows from drain to source in an NMOS transistor and from source to drain in a PMOS transistor. So this takes care of the operating point. Now the operating point is the same. That is, if let's say that mu1 Cox W by L of the NMOS transistor is the same as mu p Cox W by L of the PMOS transistor, and the threshold voltage of N and threshold voltage of PMOS transistors are exactly the same, then doing this will ensure that the operating point conditions are exactly the same for PMOS and NMOS except for a reversal of polarity. Of course, these conditions are not always true. Okay. So what happens is that this new circuit will be identical if the parameters were the same, but because parameters are not the same, the conditions would have changed, and that you can fix by changing the values of the components. Remember, the circuit topology is perfectly alright. Okay, it's the values of the components that you have to recompute. Okay, so recalculate all the values. Okay, it could be all the resistors R1, R2, RD and so on, which establish the operating point, or it's also I0 and maybe even VDD. Okay, these have to be recomputed if the parameters are different, but the topology, the circuit diagram itself is perfectly the same. Now, like I said earlier, we prefer to operate with positive voltages. That is, if we have a reference node as ground, then the supply voltage is positive. That is, we like to operate with positive supply voltages. This particular circuit operates with a negative supply voltage because this is still the reference node as I have drawn it. This is the reference node and this is a negative supply. Okay. Okay. As far as small signal picture, nothing has changed because both this and this are small signal grounds. But this is now a circuit with a negative supply. Now this can lead to complications. First of all, general preference, and also so far we have been looking at circuits which have a single transistor. We could have circuits with NMOS and PMOS transistors together. Okay. Now we can't be using positive supply for NMOS and negative supply for PMOS. That is redundant. Okay. So we would like to use positive supply for all transistors in the circuit, and that's why we have to convert this to positive supply, and that's very easily done. Okay, instead of calling this the reference node, I'll call this the reference node. Okay, so if this becomes the reference node, this is no longer the supply and this is the positive supply. Okay, so that now takes care of that aspect as well. We have now a proper circuit with a PMOS transistor with a positive supply. And finally, the way we draw circuits is normally with ground at the bottom and the positive supply on top. So all I have to do is to flip this picture upside down. Okay. If I do that, what will I get? I have R2 there, R1 there. Remember, this is the flipped picture compared to what I had earlier. That's I0. We have RD going to the bottom rail. The upper rail is this. And we have a capacitor C3 which shorts out this I0 for signal frequencies. And here we AC couple the load with C2. And now this is our common reference point. Okay. So this is the ground of the circuit. Okay. So I connect RL to whatever the ground is. So if you recall here, I have connected RL to this node. Now I'll connect it to that node because that is called the ground. And it doesn't matter for the signal picture because this point and that point are exactly the same in the signal picture. Both are small signal grounds. Okay. Like I mentioned earlier, this RL is not a physical resistor, but a representation of whatever comes afterwards, and it's always referred to the common reference node or ground of the circuit. So it is there. Okay. Okay. Fine. Then what about the input? Exactly the same. So we have C1 here, and the input is again referred to the common reference node of the circuit. Okay, and it will also have the resistance Rs. Again, this VI-RS combination is not a physical voltage source in series with a resistance, but it's a representation of what comes before the circuit, and it's referred to the common reference node or ground of the circuit. And it's very easy to see that as far as the signal picture is concerned, absolutely nothing changes, because this and that are both small signal grounds. Okay, so whether this was connected there or here, nothing changes. Okay, so that's all that's there to it. Now this circuit will look quite unfamiliar because we haven't discussed it earlier, but you should realize that this is a trivial modification of the NMOS circuit into PMOS. Okay, so with a clean algorithm like this, you can convert all the NMOS circuits that you know into PMOS, or if you come up with new circuits with PMOS, into NMOS. Okay, the bottom line is you shouldn't have any additional confusion when you see PMOS circuits. You should be able to immediately see what's happening. Okay, because we use a positive supply, these are always drawn upside down, the source is on top and so on, but that shouldn't cause any confusion. Okay, as an exercise, you can take every circuit that you encountered before with NMOS and convert them to PMOS. Okay. So to convert NMOS circuits to PMOS, obviously the functionality will be exactly the same. You reverse the polarity of sources used to establish the operating point. Okay, and of course substitute PMOS for NMOS, and if you have more than one, you need to substitute all of them. And also you could have a circuit that contains both NMOS and PMOS transistors. You can come up with the opposite counterpart where PMOS is changed to NMOS and NMOS is changed to PMOS and so on. Okay, so now again you can see something that I've emphasized earlier, that the variety of circuits is enormous. Okay, because you want to synthesize some functionality, there is a variety of choices at every decision point. Okay, like for instance, you can change the type of biasing and so on. Now you have an additional degree of freedom, you could use NMOS or PMOS. So it's extremely important to understand the logic behind the circuit and not try to memorize individual circuits. Okay, so if you do that, any circuit, whatever kind of bias or whatever kind of transistor it's using, you should be able to see what the circuit does easily. Okay, and this next part is to have a positive supply you change the ground, that is the reference, and just to follow the convention, you draw the circuit upside down. Now this is not strictly necessary, you could live with the other kind of drawing, but most of the time the drawings are done like this, with the ground at the bottom and positive supply rail at the top, so it's best to do this. Then finally, usually the input source and the load are connected to the common reference node. Okay, and this has to be changed, because first when you come up with the circuit, you see that this RL is returning to this side, which is to the side which has the source of the MOS transistor. But then when you change it to the common reference ground later, it is going towards the drain of the MOS transistor. But it makes absolutely no difference, because these two are at the same potential small signal wise. But because this is the common reference ground, it is common to return both the load and the source to this ground. Okay. And finally, what is the result? You will have a legitimate circuit, an operational circuit with PMOS transistors, but you may have to recalculate component values, because the NMOS and PMOS transistors will not have the same current factor and the threshold voltage. Okay. So you have to recalculate the component values so that you get the same functionality that you had before. Okay. And the resulting circuit will have the same small signal behavior as the NMOS circuit. What will be different is that large signal behavior will be different. And how is it different? The swing limits will be the opposite. That is, if the upper swing limit was caused by saturation in the NMOS circuit, it will be by cutoff in the PMOS circuit and so on. Okay. And just to further illustrate that, let's say that you do have a case where the current factors are exactly the same for PMOS and NMOS. Okay. And the threshold voltages are also exactly the same. So when you take the NMOS circuit and convert it to PMOS, it will be working with exactly the same small signal gain. So small signal gain, input resistance, output resistance will be exactly the same, because you don't have to change any component values at all. Okay. But the swing limits will be reversed. If the NMOS circuit had, let's say, Vi which was limited to half a volt on the positive side and minus 2 volts on the negative side, the PMOS circuit would be limited to plus 2 volts on the positive side and minus half a volt on the negative side, because the swing limits will be reversed. Okay. So that's the difference between NMOS and PMOS. And this also provides you additional flexibility. Sometimes it's more convenient to use PMOS, sometimes NMOS, which we will see when you come to more sophisticated circuits. Okay.